Hey guys, hope everybody's doing okay. What we're going to do right now is take a look at the Hydrolysis of Salts mini lab you guys completed in class. And we're going to look at how we determine why those different salts you dissolved were either acidic, basic, or neutral. So most students think of salts as just being something neutral, like NaCl, table salt, isn't acidic or basic. But as you saw in the lab, when you dissolve those in water, some remain neutral and had that green universal indicator color, and some of them were acidic and some were actually basic. So how could something that's a salt, some ionic compound, display acidic, basic, or neutral characteristics? So we'll take a look at it and see if we can figure out why the ones in your lab acted like they did. So a salt solution in general can be classified as acid, base, or neutral, which you saw. And the reason why is because the cation or anion in the salt reacts with water to create H+, which is obviously an acid, or OH-, which is a base. The reaction where this occurs is referred to as hydrolysis. So hydrolysis, hydro, you're thinking water. So it's these anions or cations reacting with water. Writing hydrolysis reactions are really easy, and it's an important part of the unit. So let's look at how we write those. Example number 1 is dissolving KNO3 in water. So let's say we had a sample of solid potassium nitrate. We want to dissolve it in water. First thing you need to do is figure out what ions are present in this salt. So you need to know some ions and nomenclature here. So one of your ions is potassium. That was K+1. And the other ion was nitrate, NO3-1. All right, so you want to make sure you have those. Next thing you want to do is figure out, would each one of these ions prefer to accept or donate a proton? Well, this is really easy to figure out. Protons are obviously a positive charge. All right, so would potassium, K+1, want to accept another positive charge, or would it want to donate a positive charge? Well, obviously potassium would want to donate a proton. It's already a +1. Potassium is not going to want to gain another proton and become a +2. We've never seen that before. So what we want to do is write an equation, write a hydrolysis equation where potassium donates a proton. So let's write that out and see what happens. So we're going to have K+1 plus water, okay, yields what? Well, actually, what I want to do here is rewrite water, and you'll see why. So let's rewrite water as HOH. It'll make more sense here. So with HOH, you have H, at the beginning. You could think of it as H+1. And you could think of the OH as hydroxide, OH-, right? So H+1, OH-1 come together to create HOH. Well, what would the potassium ion want to react with? Would it want to accept the proton? Well, no, definitely not. You're not going to make KH, right? The potassium is going to react with the hydroxide ion. All right, so what we're going to create is KOH plus what's left of the water. Well, potassium came over here and reacted with the water, or the OH, right? We have hydrogen ion left over. Okay, so let's write that here. All right, what you want to do then is ask yourself, what did we just create here? When potassium's ion reacts with water, you're going to make KOH. That is a strong base. Okay, you know that from an earlier lesson, right, on strengths of acids and bases. K is a group 1 metal with hydroxide. Group 1 metals with hydroxides are strong bases. H+ is obviously, anytime you see that, that's a strong acid. All right, so when potassium goes through hydrolysis, it creates a strong base and a strong acid. So overall, that's a neutral product, right? Strong base, strong acid, cancel out. So the potassium ion is neutral, okay? So the K+1 is a neutral ion. I screwed up my slide here. Sorry about that. So it says write the two possible reactions. We're going to do that. We already did one of them. Let's write the other one. I'll write it a little bit lower next time. The other ion is nitrate, NO3-1. All right, let's do hydrolysis. When NO3-1 goes through the hydrolysis reaction with water, it's not going to react with the OH. It's going to react with the H+. So we're going to make HNO3 plus what's left over? Well, the nitrate reacted with the hydrogen, so we have hydroxide left over. Okay, you go through and categorize these. HNO3, what is that? Well, that's a strong acid. It's one of our top 7 that you have memorized already. OH minus, okay, the hydroxide ion, definitely a strong base. Okay, it's that pure OH minus floating around there, so that's definitely a strong base. So strong acid, strong base cancel out to give you a neutral ion. So what you usually have to do here is identify which ion is acidic, basic, or neutral for both of your ions. So the K, the potassium ion, that is a neutral ion. The nitrate ion is neutral. So overall, potassium nitrate is a neutral salt solution. So if you dissolved KNO3 in water with universal indicator, it would remain green. So overall, this is a neutral salt solution because the potassium ion is neutral, makes a strong base and a strong acid. The nitrate is neutral, makes a strong acid, strong base. All right? Let's do another one. We have lithium acetate in water. So same questions here. What ions are present? Which would prefer to accept or donate a proton and write the 2 reactions? So the 2 ions present are lithium, so Li+1, and then acetate, C2H3O2-1. Okay, let's go through the hydrolysis reaction for both of these, and then we'll take things from there. So we're going to take lithium first. So we'll do lithium plus water. All right, just like the last example, lithium is going to react with hydroxide because it won't react with the hydrogen. That makes no sense at all. So we're going to make LiOH plus H+. Okay, so we're going to make lithium hydroxide, right? The lithium reacted with the OH part of water. This is definitely a strong base because we have lithium, group 1 metal, plus hydroxide. Group 1 metals plus hydroxide are strong bases. And anytime you see H+ on its own, strong acid. So overall, neutral ion for lithium. Lithium's a neutral ion. Let's look at the other one. We have acetate, C2H3O2-1 plus HOH. Obviously, this is an anion. It's negative. It will react with the hydrogen part of water. So we're going to make HC2H3O2 plus OH minus. Okay, look what happens here, guys. Let's categorize these. We have C2H3O2. You should recognize that as acetic acid. And even if you don't recognize that as acetic acid, you know it's acidic because it starts with H. And you guys say, okay, is it a strong or weak acid? Well, it's definitely not one of the 7 strong acids we memorized, so it has to be a weak acid. Okay? Anything that's not one of those 7 strong, just consider it weak. Now over here, if I write this a little bit neater here, we have our hydroxide ion. Anytime you see the hydroxide ion, you know that's a strong base. Okay, look what happens here. When acetate reacts with water, you create a weak acid and a strong base. Well, look at what happens here. Definitely the strong base will overpower this weak acid. So the acetate ion is actually a basic ion because when it goes through hydrolysis, you create a strong base. So look, lithium is a neutral ion. Acetate is a basic ion. Well, overall, this is a basic salt solution. Okay, lithium acetate is basic because you have your 2 ions in it, lithium being neutral, acetate being a base. Okay? That's all you got to do, really. You take a look at what your salt is, you break it up into the 2 ions, write a hydrolysis reaction, and see what you end up with. This one's a little confusing. It's one more. It's iron 3 nitrate. Okay, so let's do the same thing. Which ions are present? You have Fe plus 3, and you have NO3 minus 1. So on your note sheet, it tells you to write equation number 1, which is nitrate plus water first. Let's do that. So you have nitrate, NO3 minus 1, plus water, HOH. Okay, same thing as before. Nitrate is negative, reacts with the H in water, so you're going to get HNO3 plus OH minus. Okay, take a look at your results here. HNO3 is nitric acid. It's one of our top 7, so that is a strong acid. And hydroxide by itself is a strong base. So overall, the nitrate ion is neutral. We did that already. That was one of the first examples we did. Now the other one is a little bit, it's weird, okay? So Fe plus 3, look what it does here. There's this equation here on your note sheet. Even on your handout, in your note packet, it says, see the illustration on the next page. You're not required to write this equation, okay? So don't lose your mind here about this. But you need to know why hydrogen, or H3O+. You need to know why that's formed, okay? Iron 3 is not a group 1 or 2 metal, all right? So it just acts a little bit differently. You could still take our shortcut here and write Fe plus 3 plus HOH produces FeOH3 plus H plus. Now this isn't balanced, but you could balance it if you wanted to. Since iron isn't group 1 or 2 metal, with hydroxide, it has to be a weak base, and H plus is a strong acid. So this is acidic, an acidic ion. Okay? The Fe plus 3 is an acidic ion. This isn't exactly what happens though here. Okay, I mean it's kind of close, but it's not exactly what happens. What you end up happening is this reaction here that you don't need to know. So if you want to just figure out is iron 3 acidic, basic, or a neutral ion, just do the hydrolysis reaction like I taught you, and you can see that strong acid overpowers a weak base. So overall, iron 3 nitrate is going to be acidic. Okay, because you have a neutral ion, which is nitrate, acidic ion, which is the Fe plus 3. The next couple slides will go through and explain why this ion is acidic with a little bit more detail. It's something called a Lewis acid, actually. So we have another definition of acids. Now I'll just start this by saying Lewis acids and bases are not on the AP test, but I feel like it's something I should show you so you have this background for when you go to college. So the Lewis definition is another one that we could add to Bronsted-Lowry and Arrhenius, and it's a little bit more inclusive than Bronsted-Lowry. So if you remember our definitions of acids and bases, the Arrhenius definition is the least inclusive, Bronsted-Lowry includes more things, and now Lewis definition will include even more of them. And it takes the viewpoint of the electron pair instead of the proton. So even as I teach this, I always say the wrong thing, because I'm so used to saying proton, 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 and hydrogen. That's what we're usually focused on with acids and bases. But for Lewis acids and bases, we're focused on the electron pair. So for a Lewis acid, it's going to be an electron pair acceptor. And for a base, it's an electron pair donor. Okay, must have a lone pair. So anyway, that's the main definition here. Next thing that it says is that many Lewis acids would not be considered acids under the Arrhenius or Bronsted definition. And you can see that as an example from our previous slide here. Fe plus 3, we said was an acidic ion, but Fe plus 3 would not be considered an acid for Arrhenius because it doesn't have a hydrogen. Same thing for the Bronsted definition. Bronsted definition is that it's a hydrogen donor or proton donor. Well, Fe plus 3 has no hydrogen to donate, but you could see that it is actually an acidic ion. So this just adds more acids to our list, basically. So let's take a look at why. Some metallic ions, like Fe plus 3, when they dissolve in water, are acidic. So why does that happen? When they dissolve in water, they attach to the water molecule and they accept the electron pair on oxygen. So you remember, oxygen has 2 lone pairs on it, okay? And a Lewis base, if you go back here, a Lewis base is an electron pair donor, and an acid is an electron pair acceptor, all right? So we're going to focus on Fe plus 3, or our positive ion, accepting an electron pair from the water. Okay, so here is our ion, okay, our positive ion, right? It's going to accept the electron pair from the oxygen. Okay, so it would make this an acid, right? That's our electron pair acceptor. And down here it says the higher the charge and the smaller the radius, the more acidic. So the higher the charge on your positive ion, like look, here's our plus 3 charge, and the smaller it is, the more acidic this is going to be. because it can attract that lone pair. It can attract the lone pair on that oxygen really, really, really well, being a high positive charge and a small size. If you use something that's larger in size and a smaller charge, the attraction between the lone pair on the water and that ion is pretty weak. Okay, so it's not going to attract that lone pair very well. All right, so let's look at another an image here to better explain why some of these positive ions are acidic. What happens? This is known as hydration. Okay. All right, so let's take a look at this image here. We're going to look at and focus on aluminum. All right, so aluminum has a +3 charge. We know that. And if you have the aluminum ion, it's going to attract water molecules to it, right? If you looked at the water molecule, you have your partial positive on the hydrogens, and your oxygen is your partial negative, right? That partial negative, where the lone pairs are, is going to be attracted to your positive Al +3. Okay, opposites attract. So, like I said in the previous slide, the larger your charge is, the more, the better attraction you have. So, you have all these water molecules attracted, and what you end up with is a pretty strong attraction here between the aluminum ion and your oxygen. Now remember, there's a bond between O and H here. Okay. This goes back to a previous lesson on the strengths of acids, the inductive effect, if you remember that. Because this pull is so strong right here, okay, this oxygen is getting pulled in so well to aluminum, it actually weakens this bond, okay? Okay, it's going to weaken the hydrogen-oxygen bond right here. When that bond is weakened, the hydrogen, which is right here, is allowed to come off, right? So this bond breaks, okay? The hydrogen comes off, and you create H+, or in this image, there's another water molecule here, and the H goes to that water molecule and creates H3O. Okay, the point is, this is a strong acid. So it's going to create a strong acid, H3O, H3O+. Look what's left. You have this OH group kind of attached to the aluminum. So if you go back to the equation here for iron 3, which is where this all started, this right here is your iron +3 with the hydration shell, all those waters surrounding it, okay, plus water. And look, you end up with H3O, like I showed you, okay? And look, you have this weird equation here. So your hydration shell, you had 6 water molecules around it. Now you only have 5 and a weird OH group, all right? So if I go, drive you nuts here going back and forth with all these slides, you can see here, here it is. Here's the 5 water molecules, okay, 1, 2, 3, 4, 5. And here's your OH chunk right here. Okay, and the overall charge, because this OH is minus, it becomes a +2 ion. All right, so remember, you're not responsible for writing these equations. I just want to show you that when you have a positive ion like this, it attracts the oxygen, attracts that lone pair. Okay, that's what makes it a Lewis acid, and it ends up creating this H3O substance. All right, so this is going to work for ions with a large charge. Okay, so the bigger the charge, the better it's going to be here, and generally a small size. All right, and that trend is coming up on your note sheet. All right, so I have the extra additions here. Electron density is drawn towards aluminum. It helps break that OH bond to create H3O. So here's the overall equation once again. I already talked about that. And this is just another summary of what was going on there. So just another image here. You can see the actual ball and stick model here of your aluminum or iron 3 ion here in the middle. Okay, and how those water molecules are attached, and how this bond right here, okay, breaks, and you can create your H3O. All right. Generally, the greater your charge and smaller your size make the cation more acidic. So it is a general trend. Not all of them follow the rules because there's a million different exceptions and things that go on here. But generally, if you compare iron 3 and iron 2, iron 3 has a +3 charge and iron 2 has a +2 charge. You can see here's iron 2 and here's iron 3. And look at that Ka difference. You have to the -3rd power and times 10 to the -10th power. So Fe+2 is definitely weak acidic ion, and iron +3 is still just a general weak acid. You know what I mean? So Fe+3 is a stronger acid than Fe+2. You know, in the grand scheme of things, they're still both pretty weak, but iron 2 is weaker. So the higher the Ka, the stronger the acid. You know that already, and it's because Fe+3 has a stronger attraction to those water molecules. Right? It pulls the water molecules here in more, right? And weakens that bond more so it could break. Fe+2 wouldn't pull in on these waters as much, so this bond wouldn't be as weak for the hydrogen to break off. Okay, general trends here for this. You know, this could be a little bit confusing here, but it doesn't have to be. All right. You could just do what I taught you, and you could go and take your salt, okay? Take your salt, split it into the ions, and write your hydrolysis equations, all right? And then compare the two ions. It's like you did on the first part of the note sheet here. Here are some general patterns, though, to help you do it a little bit quicker if you're trying to do these fast and you don't have time to write out all these hydrolysis equations. Number 1 says an anion, that's the conjugate base of a strong acid, will not affect the pH. So if you have your 7 strong acids, right, you have HCl, HBr, HI, and then your oxo, or your oxy acids that are strong, like HNO3, H2SO4, there's a couple other ones there, HClO3, HClO4, that rounds them out. Any of these anions, so Cl, Bri, NO3, SO4, ClO3, and ClO4, if you see any of those ions, they are neutral, okay? Because think about it. If you had HCl, take your Cl ion, right? Do hydrolysis. Look what you get. You get HCl plus OH minus. You have a strong acid, strong base, cancel out, okay? It'll happen for every single one of these, all right? So if you see any of those negative ions, Cl, Bri, NO3, SO4, ClO3, ClO4, they are neutral ions. Okay, they're not going to affect your pH at all. All right. Now that's easier than writing the hydrolysis equation. Now sometimes you have to write the hydrolysis equation because the question tells you to. But if it doesn't tell you, you don't have to. Okay, so an anion from a strong acid won't affect the pH. It's not going to want to gain any hydrogens. If you go back to Cl minus, right, you're going to make HCl plus OH minus. Well, remember, like, this is a strong acid, HCl, so it's not even going to, like, it looks like the Cl minus will attach to this hydrogen and make HCl, but immediately it's going to dissociate, right, into H plus and Cl minus, and you still have HOH, or I'm sorry, you still have OH minus and H plus to make water. All right, so there's no way this hydrogen and this chloride are going to come back together, all right, because HCl is a strong acid, and the definition of that is it remains dissociated and wants to dissociate completely in water. Okay, so if you go back to the chart here, number 2, it says an anion that's the conjugate base of a weak acid will increase the pH. So the example here is NO2 minus 1. So let's write that out just to prove it to you. NO2 plus HOH, if you're not sure, do the hydrolysis equation. The NO2 minus will react with hydroxide, so you'll have, it'll react with the hydrogen. Going too fast. All right, so you'll have HNO2 plus OH minus. Okay, HNO2 is acidic, but it's a weak acid. It's not one of our 7 strong acids. And OH is a strong base. So look, you have weak acid, strong base, basic ion overall. So nitrite ion is a basic anion, all right, which of course would make the pH go up because the higher pH, the more basic. So it says produces hydroxide. There it is. Okay. So any anion you see that is not from your strong 7 is going to be basic. Okay? It's going to produce hydroxide, increase the pH. Okay, the last two are for the cations. A cation that is the conjugate acid of a weak base will decrease the pH. It'll produce H3O. So you're talking about non-group 1 and 2. So this is what I just went over. So if you have something like aluminum, okay, it's an Al plus 3, plus water, okay, you can get aluminum hydroxide, plus H plus. Okay? Sorry. Weak base, strong acid, acidic salt overall. Decreases the pH. Alright? This is where you make your hydration shell. Alright? What I went over on the previous slide. Okay? So cation, that's the conjugate acid of a weak base, will decrease the pH. So basically, if you have a cation that is from anything other than group 1 and group 2, it will be acidic. All right? That's a Lewis acid. Okay? And then finally, group 1 and 2 cations will not affect the pH. That's the last one on here. So group 1 and 2 are your cations that will combine with hydroxide to make a strong base. So an example would be sodium. So Na plus 1. Okay, if you're not sure, do hydrolysis. You have NaOH, because the Na will react with the OH, plus H plus. NaOH is a group 1 plus hydroxide, strong base, H plus, strong acid. Okay, they cancel out, neutral, just like it says here. Okay, substitute any other positive cation into there from groups 1 or 2. Do lithium. Okay, look at that, same thing. Lithium plus water gives you lithium hydroxide, strong base, H plus, strong acid, neutral. Okay, group 1 and 2 cations won't affect the pH. They will not make that hydrolysis shell. They are the charges are too small. Okay, so what you'll end up with is just a neutral salt or a neutral ion if you have any of those. All right. So take some practice, okay? And that's the best way to go through this. Go through, do some practice problems, see the patterns, and then, we'll do these a million times in class. You'll get the hang of it. So let's wrap it up here. Oh, there we go. Too small and too low of a charge, because group 1 and 2 cations are plus 1s and plus 2s. So no hydration shell will be created. If a solution were to contain both a weak acid and a weak base, and you would see what is created, you have to look at your Ka and Kb values. So there has to be some more context within the problem for you to actually solve these, if you end up with something that isn't very obvious at the end. All right? So to wrap it up, compare the strength of the Lewis acids on the screen here. I have 4 different solutions with these various salts dissolved in them. You can see the pH values here. So you want to figure out which one is which. Okay, match them up. So obviously this is a pH of 7 in blue here. It's a different indicator that we're using. So which one of these 4 salts would be a completely neutral solution? That's what you want to figure out. And then which one would be basically neutral but has a chance to be slightly acidic, and even more acidic for the pH of 6.9, 5.5, and 3.5. So take a second, go through and try it, and then we'll wrap it up. All right. So the pH of 7, you want to look at what we end up with here. Aluminum nitrate, calcium nitrate, zinc nitrate, sodium nitrate, all of them have nitrate. So automatically, the nitrate isn't really going to make a difference here in any of these. If you weren't sure, you could look, we did this like 4 times now, nitrate plus water. Okay, if it goes to the hydration equation, you get HNO3 plus OH minus. So that's a strong acid, strong base, cancels out. So the nitrate ion is neutral. Okay, so we don't need to worry about, that at all. We want to focus on the cations that are here. All right, so let's do that and see what we end up with. So this is neutral, 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 neutral. All right. Aluminum, you have Al plus 3. Okay, if we go back to our rules on the previous slide, that would fall into this category. A cation that is the conjugate acid of a weak base will decrease the pH. So it will be acidic. So a non-group 1 and 2 cation will be acidic. Oops, wrong way. So this is going to be acidic right here. Okay. Go to the next one. You have calcium. Calcium is a group 2 ion. So we're here. Okay. Group 1 and 2 cations will not affect the pH. All right. So this is basically neutral. All right. Zinc nitrate. Zinc is a plus 2. And if you go back here, it falls into this category right here. Okay, it's not a group 1 or 2 cation, so it will also be acidic. Let's label that. And then you have sodium. Sodium is in group 1. It says group 1 and 2 cations will not affect the pH. So this is also neutral. Now you're saying to yourself, wait a minute, both of these, calcium and sodium, are neutral. You have a pH of 7 and 6.9. Well, if you look at these two, sodium is only a plus 1, and calcium is a plus 2. All right, so which of these has a better chance of being neutral? It's definitely Na plus 1. So we have the NaNO3 going over here. Okay, there's still hardly any chance of this calcium ion being a strong acid or very acidic at all, but it's a better chance of being an acid than the sodium nitrate because the charge is higher, so there's a little bit better chance of making that hydration shell. Okay, now the last two you want to look at is zinc and aluminum. Zinc is a plus 2, aluminum is a plus 3. We did say with Lewis acids, because that's what these are. Okay, Lewis acid. Both of those are acidic, obviously, but you want the higher charge to be more acidic. So zinc is a plus 2, so that will be a little less acidic than the aluminum, which will be your pH of 3.5. Okay, so basically all of these are, well, the zinc and aluminum are your Lewis acids. Your sodium and your calcium, for all intents and purposes, are neutral salts. And these are both acidic salts. There are no basic salts in this because the pH that was the highest was 7. All right, so what you can do now is you can ignore this right here for the quiz. The quiz is scheduled for whenever. You'll eventually see when it's scheduled for if it's not announced already. But you could complete part 2 of the Hydrolysis of Salts mini lab. You can work on that for homework. You might do some of that in class as well. And obviously pages 29 and 30, the strength of acid-base worksheet. I think that should be done already. Okay. So anyway, it takes care of the hydrolysis of salts lesson here, and we'll talk about it more in class if you have any questions. Thanks, guys.